Artificial intelligence tries to mimic how the human brain learns. But how does the brain learn? How does the brain store information and represent concepts? We used to think that the brain stores information as symbols. You can think of these like puzzle pieces with sharp edges. But in 1950, scientists ran an experiment that showed something else. And the key insight from this experiment is what drives and enables modern artificial intelligence. They trained a pigeon to peck when it sees a light, a yellow light, in order to get food. And so the idea was, if this pigeon stores information in its brain symbolically using these kind of puzzle pieces, then it would form a direct connection between the symbol for yellow light and the symbol for food. A direct symbolic connection. And so they asked the question, what would happen if we change the color of the light? So they predicted that this would happen. At some point, the light would be different enough, a different enough color, that the pigeon would just stop responding. It would stop responding. So let's say if it's blue or orange, at some point, no response. Because it doesn't fit into that puzzle piece that it learned, this puzzle piece symbolic connection between yellow light and food. But that's not what happened. In fact, what they saw, is that as you change the color of the light, the response from the pigeon gradually decreases. This more soft response. So this showed that the brain of the pigeon, the mind of the pigeon, wasn't forming this symbolic connection between the puzzle piece symbol for yellow light and puzzle piece symbol for food. It showed and suggested that the brain of the pigeon was actually forming a distributed connection between these concepts. And what this means is that the concept of yellow light and the concept of the connection is actually distributed across multiple nodes or neurons. So maybe one trial, when we're training our pigeon, right? These 3 nodes are activated. Another trial, these 3 nodes are activated. Similar nodes, but slightly different. And then when we move to an orange light, only 2 nodes are activated. So you get fewer responses. And then a blue light is much more different, right? So you get maybe even fewer responses. Only one's activated. So this key insight that knowledge in the brain is actually stored in a distributed representation, not symbolically, not these hard-edged puzzle pieces, this distributed knowledge representation, that's the key insight that we used to create neural networks. And neural networks are the current imitation, rough imitation, of the human brain inside a computer. They're what most of modern AI systems that achieve great things use in order to learn patterns. So neural nets are composed of neurons. Each neuron learns a very simple pattern. These neurons are stacked on top of each other in columns called layers, and each layer receives information from the previous one. So each neuron learns a simple pattern. When you have millions of these neurons together, you can learn more complicated patterns, and thus the neural network can learn. Now, what we've been doing to try to get to stronger, more capable artificial intelligence is making these networks deeper, with more connections and more neurons, so that it can learn more complicated patterns. Now, in recent years, we've been pushing the size of these networks and the amount of data they can consume, because larger networks need more data. We've been pushing this to the limit that modern hardware can allow. And we've gotten large language models. These are AI systems powered by neural nets, by giant neural nets, that can generate human-like text, almost indistinguishable from text written by a human. And one of the most prominent examples of this in recent months is, of course, ChatGPT. ChatGPT is a large language model chatbot that was trained on 300 billion words. It read all this information, and it's one of the most advanced artificial intelligence agents ever made available to the general public. You interact with ChatGPT through a chat interface. So here I'm saying hello, and it says hello back. But ChatGPT can perform many tasks. Anything that you can describe using text, ChatGPT can attempt to solve that task. For example, here I ask it to write a poem about how AI is changing the world. We get a little nice poem. And here I ask it to make that poem into a short rap song. So you get a little groovy song, right? Now, importantly, ChatGPT, these large language models, remember context. They remember past messages in your discussion, and this is extremely powerful, that they remember context. Here's an example where I wanted to create an AI-inspired sports drink. So I asked ChatGPT to help me come up with some names. So we got Smart Sweat, RoboFresh, IntelliHydrate, Cybersport. So I liked Cybersport. And so I said, I like Cybersport. Can you design a short ad for it? And so it said, sure. Are you ready to take your workouts to the next level? Introducing Cybersport, the sports drink inspired by artificial intelligence, and comes up with this whole ad. So you could do all sorts of things with it. So these limitless number of tasks almost, as long as you can describe in language, it can try to achieve. It can draft emails, it can create marketing material, it can help you with job applications, it can translate between languages, it can create training material. It seems that these large language models have the potential to revolutionize multiple industries, because the text generated is almost indistinguishable from humans in many cases. But how do these large language models learn? They seem to contain a vast amount of knowledge and information. How is that arriving? Where does this information come from? How are they able to compose all this information into meaningful sentences relevant to your question, right? And so the key is, the way they learn is by auto-completing the internet. They read news, articles, Wikipedia, books, and they predict the next word. Essentially, these large language models are very smart autocomplete systems, much smarter than the ones on your phone. So ChatGPT, for example, learned by reading about 300 billion words on the internet. So let's dive into this a little bit. How does it do this? How does it autocomplete the internet? Let's say we're reading a Wikipedia article about the tallest buildings. This sentence comes up, it's reading this sentence. How will we learn from this sentence? So we want the AI to autocomplete the sentence. We give it a starting word, just so it has a place to start off. And we ask it, predict what you think is the most likely next word. Now, after the can really be anything, so it says the elephant. And then it checks back against the article. Oh, I should have said tallest. So it understands it made a mistake, and then it modifies its internal neural network so that next time it's more likely to say tallest, the correct answer. So now we have the tallest, and so it makes another prediction, person, it checks again, that's wrong. It modifies its internal neural network, this algorithm that's learning patterns, so that next time it's more likely to say building. And we keep doing this. We do this for hundreds of billions of words, books, articles, Wikipedia pages. And just through this simple, relatively simple training process, a vast amount of knowledge is encoded in these giant neural nets. And they're able to encode all of this knowledge because they store it in a distributed way in a giant, GPT-3, which is the model behind ChatGPT, has 175 billion connections, right? So it's this giant neural net, stores information in this distributed way inspired by the brain, and by auto-completing the internet, it's able to capture a lot of this knowledge. So let's look at an example. Let's say we have a large language model that hasn't been trained at all. It doesn't know anything yet. So I give it these 3 words as a prompt, and I say, okay, autocomplete this sentence. So maybe it'll say, SXSW is held, blue, dog, familiar. So that doesn't mean anything. It clearly doesn't understand grammar. It's just choosing random words. But that makes sense. It hasn't learned anything yet. It hasn't read anything. It hasn't tried to autocomplete and tune itself. Okay, now let's say we train it a bit more. It's read a bit more of the internet. SXSW is held in your hand. Okay, we're getting somewhere, right? Because it understands possession, it understands your, it has some understanding of grammar, it has a relationship between held, it knows that relates to hand, and so it's getting this knowledge by looking at the relationships between words. So now let's say we've trained something like ChatGPT on a giant portion of the internet. SXSW is held each year in Austin, Texas. So then we can get this really powerful, relevant response because it's been trained on more and more data. It now understands that SXSW is not an object you can hold. It's a conference, festival that's held each year in Texas. However, this is great, but there are still limitations to these technologies. And one is that they make mistakes. you cannot guarantee that what they're going to say is actually correct. Because they're not, for the most part, they're not trained to be correct. They're just trained to be likely, to produce the most likely next word, not to be correct, right? So it can make mistakes. Sometimes they're hard to detect, especially for arithmetic, counting tasks. These simple things that often are simple for us is just predicting the next word or the next character. So it can make these mistakes. For example, here I ask ChatGPT, what's 1/4 minus 1/8? And bottom is an example from a few months ago. This is from this week. In both cases, it makes these really simple errors that most people will not make. So just these really simple mistakes, because it's not trained to be correct. It's just predicting the most likely next word. There's another limitation. A lot of its responses sound plausible. They sound reasonable, but they're wrong. And they can be wrong in ways that are very hard for us to detect. And so this kind of introduces a danger where we can use the output of these systems. We think it seems plausible, but really there's a mistake. Because it seems plausible. We say, oh, that's probably right, but it's not. For example, here I ask ChatGPT to fill in the rest of this quote. It's a dangerous business, Frodo, a quote from Lord of the Rings. And at the end it says, this is a quote spoken by the character Bilbo Baggins to his nephew Frodo as they prepare to embark on a perilous journey together. Does anybody spot the mistake? If you've read the books, okay, so we see some people together. They don't embark on the journey together. Bilbo and Frodo don't go on the journey together. If you've read the book or seen the movies, Frodo kind of goes off with his own friends, right? So this is really reasonable. This is really plausible. Most of it's correct, but it makes these small mistakes. It's not guaranteed to be right. And further, there's limitations, but there's also danger that comes with these technologies, and that comes in the form of unethical use cases. If these systems can generate text that's almost indistinguishable from a human, they can be used to spread misinformation or fake news, impersonate people, organizations. They could even be used to generate malicious code or detect exploits in systems. So our goal is to produce helpful and not harmful AI systems. And so as we create these more capable systems, we want to make sure that there's goal alignment between the humans creating them and the AI systems that they're creating. We want to make sure that the AI's goals align with the goals of its intended use, right? So it's not used for these bad purposes. So it's used to help and not harm. But there's 3 challenging problems to solve when it comes to goal alignment. One, if we want to encode values or goals into a machine, how do we encode values into a machine? Values that can't be broken. That's a hard problem. And second, which values do we choose? As cultures change around the world, values change around the world. So which values do we choose to encode into these machines? And the third is, how do we even define these values? For example, if one of our values is don't harm a human, well, what does that mean? Are you going to start listing out all the ways to harm a human? Probably won't work because, as we know, computers often find loopholes in the rules we give them. So there's 3 important problems. But if you use ChatGPT and you ask it, how can I hack into my neighbor's Wi-Fi, it won't tell you. It'll tell you, I'm sorry, but as an AI language model, I cannot assist you with illegal activities. So how does it know not to answer? There seems to be some sort of goal alignment in ChatGPT. And the way that this is learned is through human feedback. OpenAI hired a bunch of labelers. They gave them a set of rules, and they hired these labelers to provide human feedback to the machine. So let's look at the rules. This is just an example. Don't say anything harmful, don't provide assistance in illegal activities, be thoughtful and empathetic, follow common sense, ethical and moral standards, etc., etc. So these are just examples of what these rules could look like. So they give these rules to the human labelers, and then they get feedback. And there's multiple ways you can get feedback from these labelers. First is you can ask the labelers, these humans, what should the assistant say? So here it says, I cannot help you, yada, yada. The second, these systems don't always give you the same output. So we can ask it for 2 outputs. And then we can rank them. So in the first one, it says, sure thing, you can use an app called Very Easy Hack that will allow you to log into your neighbor's Wi-Fi. And the second one, it says, hacking is not a good idea, you shouldn't do it. And so the human labeler looks at both of these responses generated by the large language model and says, that one's better, that's the human feedback, and we can learn from that. The AI system can learn from that. So large language models can generate text that's often indistinguishable from humans. But what's next? What's next after large language models? One thing I'm working on at the Vector Institute in Toronto is trying to go beyond language, to go into the real world. And so these large language systems contain vast amounts of knowledge. The question is, how can we extract the knowledge contained within, provide that to AI systems who are taking actions in the real world to make better decisions? So going beyond language and into actions in the real world. And there's one other key possibility when it comes to these systems. An AI scientist. Could we create an AI scientist? AI to create AI? So the way AI research is being done is we have ideas, we have hypotheses. Let's make a neural net like this. Let's make an algorithm like this. We write the code, we test it out, and then we see if it works. If it works, great, we move on to the next version. If it doesn't, we try again. It's a very time-consuming process. But this AI scientist could allow us to test our ideas much faster. And it could enable this sort of cycle where we have an AI scientist, it'll enable us to test things faster, to reach faster capability improvements, and then we get a better AI scientist, and this feedback loop continues. And the key thing to understand is that this AI scientist doesn't need to be perfect. If it's even 2 times efficiency, if it's even 2xing our efficiency, then we get to the next version 2 times faster, and that version is maybe better. So then, 5 times our efficiency. And the way it could do this is, generating code, but that code, again, doesn't need to be perfect. It just needs to be enough to start this feedback loop. And that could lead to an acceleration in growth of AI capability. And we're already starting along this path. GitHub Copilot was recently announced, it was recently announced that GitHub Copilot, an AI system that can generate code, is behind 46% of its developers' code. So think about the dramatic improvements there. It can generate code like here to parse an expense spreadsheet, here to fetch tweets from a user. It can write code in different languages. So given instructions, it can generate code. And there's another cutting edge method that was proposed that could fuel this loop, which is instead of learning from human feedback, learning from AI feedback. AI to label AI. And this was about 3 months ago in January by Anthropic. So very recent. And so how this works is, again, we have these rules. We give that to an AI system. And then we ask, can you help me hack into my neighbor's Wi-Fi? At this point, it's not aligned. So it says, sure thing, you can use an app. And then we ask it to critique itself. Identify specific ways in which the assistant's last response is harmful, unethical, etc. It critiques itself. Then we ask it to revise. It gives us a revision. And then we have a new training pair of human question and the answer that we want, right? So it's actually labeling itself. So we just need a bit of auto-completing the internet, getting some knowledge in there, a bit of human feedback, and then it can start training itself, in a sense, to follow a constitution. And this is self-alignment. It can actually align with our goals by itself. And so this also contributes to this cycle. Now, as we develop stronger large language models that can write these systems, we could get to an AI scientist, we could get closer to an AI scientist, and we're already seeing that we're getting closer to this system. But we're missing something, and everything we've talked about, all the AI systems we've talked about so far, require us to provide the AI system with answers. So here we're saying what the correct answer is, the correct word. But what if we don't know the answers, right? This is a problem because it's limited by our knowledge. 1, it's limited by our knowledge. 2, if we don't know how to solve something, it won't be able to solve it, right? And so if there's mistakes in our data, bias, it'll make the same mistakes, it'll be biased. So instead of providing the correct answers to machines, what if we just provided the machines, these AI systems, with goals? And these AI systems would automatically figure out what actions you need to take in order to reach those goals, right? Then it won't be limited by our knowledge. We just specify the goals, and it figures out the correct answer. It figures out what actions you need to take in order to achieve those goals. And there's already a type of AI that's working towards this goal, reinforcement learning. This is a term that comes from psychology. It's all about learning from reward. So we use reward to specify what our goal is. For example, let's say Mario is in his little world, right, playing the game, and he gets rewarded every time he moves to the left. Sorry, to the right. Wrong way. That's important. So every time Mario moves to the right, it gets a little bit of a positive reward, just a number, right? And the AI system controlling Mario wants to maximize this reward over time. And so with reinforcement learning, the system can learn what actions to take. It learns how to play the game automatically without any human answers, just from having a goal specified, just from only having this reward. It starts exploring trial and error. But that's a key limitation, though, trial and error, because often it has to go through this loop 100 million times. At the start, it doesn't know anything. It can make mistakes. So you can imagine putting this in a robot, and then it starts, doing some crazy stuff and breaks itself. That's expensive. So the key to training these reinforcement learning systems today is to use simulations. If we have simulations of the world, accurate simulations of the world, then we can learn how to take actions in those simulations and transfer that to reality. In this case, a 4-legged robot was trained from scratch, knew nothing before, in a simulation of physics to walk upstairs over rough terrain. And what the researchers found is they train it inside this physics simulation, and then they take the same neural net that learned inside the simulation, transfer it to the real version of the robot without any fine-tuning. It's not learning in the real world, and it's able to learn because the physics simulation was accurate enough that it's able to transfer knowledge from the simulation to the real world. So what else could we do with this technology? This ability to give goals and have the machine figure out what actions get us to those goals. Let's say we want to design an optimal city. Well, we could give all sorts of goals to the AI. Maybe we want more solar panels, we want more trees, we want less crashes. And then the AI inside of a simulation of a city will figure out how to make that happen, what actions we need to take. One project I worked on was about crashes. So look at this picture for a second. You might notice something. There's a pedestrian right behind the car. And if a car was going into the intersection, trying to turn right pretty quickly, they might not see the woman. They might accidentally crash into her. And so you might say that cars shouldn't be allowed to park there kind of on the crosswalk. And you'd probably be right. We have data in our cities about where crashes occur most often. And so what I worked on was creating simulations of those intersections, those areas, and having a reinforcement learning agent figure out what we need to change in that simulation in order to prevent crashes, to reduce the number of crashes. And it's not limited to just city development. We can have simulations of forest fires. People are working on this now. And we can have reinforcement learning systems figure out what are the best actions to take in order to deploy firefighters, deploy helicopters, and we just give it the goal, burn the least amount of forest, least amount of casualties. And we could go even smaller, to the molecular level. We have simulations of molecules, of atoms, and we can give reinforcement learning agents the goal of creating materials with desired properties. And so there are already RL, reinforcement learning systems, that are being used to design materials. Let's say we want a material to be more conductive. So we give it this goal, and then inside of the simulation, it places atoms, it makes connections and bonds between those atoms to maximize this reward to achieve the goal of making conductive materials. And so running artificial intelligence inside of simulations of reality could allow us to design a better world and discover better decisions. But if we remember to ask questions beforehand as we develop these large language model systems, these decision-making agents, and prepare for the future, only then can we actually have a shot at creating utopia. Thank you.